How exactly did life start on Earth? How did things go from being plain old chemistry, atoms, molecules, gases, to actual living organisms that grow, eat, reproduce, and eventually complain about Mondays? It's a question we've asked for centuries, and the answer might be stranger, slower, and more indifferent than you'd expect. Tonight, we'll follow that story, from the quiet laws of physics to the messy chemistry of life. Life, as we know it, is built from carbon, hydrogen, oxygen, and a few other bits thrown in for variety. These are the same elements found drifting in clouds between stars or locked up in dead rocks. There's no magic ingredient. And yet, under the right conditions, these elements arrange themselves into something that could copy itself, use energy, and, eventually, invent reality television. Which makes you wonder how Earth, around 4.5 billion years ago, was a hostile lump of rock, boiling with volcanoes, constantly bombarded by space debris, and absolutely devoid of anything resembling a picnic. No oxygen in the air, no green fields, just gases like methane, ammonia, water vapor, and carbon dioxide. It wasn't lovely, but it was full of chemical potential. The stage was set for an experiment, with no plan, no purpose, and no one watching. Somewhere in all that chaos, molecules began to form more complex structures that could break down energy, link up into chains, maybe even copy themselves imperfectly. It sounds unlikely, because it is. But here's the catch. The universe isn't in a hurry. If you give something billions of years, and a planet-sized chemistry lab, you'd be amazed what can eventually go wrong just right. What's truly humbling is this: none of it needed direction. The atoms didn't vote. The molecules didn't set goals. There was no foresight, just energy interacting with matter under strict physical laws. Eventually, some molecules happened to persist. Some systems happened to become more stable. That's it. The rules of the game didn't change, but the players started doing more complicated things. Of course, the idea that life began as an accident doesn't sit comfortably with everyone. People like purpose. We like things to mean something, but nature doesn't really do meaning. It does repetition, scale, and staggering amounts of time. And life? Well, life just happens to be one of the things that came out of all that. Tonight, we'll explore how those conditions came together, what chemicals were involved, what processes may have taken place, and why it's all even remotely possible. We'll also take a look at the scientific work done to make sense of it all, and why even today we're still piecing the puzzle together. This leads us to consider why this question matters, not just to scientists, but to you, a person made of atoms that used to be part of a star, or a rock, or a puddle of pre-life soup. At the heart of tonight's journey is one simple question. How did life on Earth begin from what was, by all appearances, a collection of lifeless chemicals? It's not just curiosity. It's something deeper. We want to know how we got here. How molecules that don't care about anything manage to end up forming something that can care about everything. It's tempting to imagine a moment of creation, a spark, a blueprint, a tidy sequence of steps leading neatly from A to B. Unfortunately for anyone hoping for a clean story, the truth is messier. Life's beginning was not a designed event. It was a chain of chemical reactions, nudged by energy, time, and sheer probability. In short, it was an accident, just one that happened to keep going. What makes this question especially difficult is how much of it sits in the past. We're talking billions of years ago, before fossils, before DNA, before anything could leave behind evidence we can easily recognize. Much of what we know is based on clues like ancient rocks, chemical residues, or recreated reactions in labs. We are reconstructing a process that left no eyewitnesses. And yet, there are patterns. All life on Earth shares certain traits. It uses the same basic molecules, follows the same genetic code, and depends on energy from the environment. This suggests a common origin, a starting point somewhere in that messy soup of early Earth. If we can understand how the first building blocks came together, we can begin to understand why life is the way it is now. The question also matters because it connects science's most basic fields, chemistry, physics, biology, into one shared puzzle. What conditions are needed for life to emerge? What's the role of water, of temperature, of minerals? Could it happen elsewhere? The deeper we look, the more we realize life might not be a rare miracle, but a natural result of the laws of physics applied with enough time. It's also humbling. There is no evidence that life was supposed to happen. The universe didn't roll out a welcome mat. Earth wasn't designed with an instruction manual. If anything, the fact that life exists is proof that nature doesn't need guidance, just persistence, energy, and quite a lot of time to get things wrong before something finally works. Of course, none of this is fully settled. There are competing ideas. RNA first, metabolism first, hydrothermal vent theories, and more. What unites them is the understanding that life did not leap into being fully formed. It crawled out of chemical disorder, step by tiny step. The details are debated, the principle less so. This leads us to consider how this question touches your life directly. Because the chemicals that became life didn't stop evolving once they got started. They're still doing it now, inside you. You are, right now, the result of a few billion years of accidents. Every cell in your body, every breath you take, and every thought you've ever had, all depend on chemical reactions that once happened by chance. It might not sound romantic, but it's true. You are chemistry that somehow didn't stop reacting. And that makes the question of life's beginning oddly personal. Think about the basics. You eat, you breathe, you grow. None of these things are magic. They're just a series of chemical reactions, repeated again and again, in the right order, by the right molecules. Your body runs on instructions written in DNA, which is really just a molecule telling other molecules what to do. It's efficient, if not particularly chatty. Yet it's easy to forget how strange this all is. Most things in the universe don't breathe. Rocks don't metabolize. Stars don't replicate themselves using genetic codes. And yet here you are, built from the same atoms as stars and rocks. Managing to be hungry, tired, and occasionally emotional over supermarket sandwiches. It's tempting to think of life as something separate from the rest of nature, something elevated or special. But chemically speaking, there's no hard line. The building blocks of life, carbon, hydrogen, oxygen, nitrogen, are common. The difference is in how they're arranged. And how that arrangement started is frankly the awkward bit we're still trying to piece together. Most of what you do each day relies on processes that began in the earliest forms of life. The way your cells divide, how your body processes energy, even the enzymes breaking down your dinner, all of it can be traced back to systems that evolved from simple molecules with no agenda whatsoever, which makes your daily routine, school, work, scrolling, part of a much older chemical habit. Of course, none of this answers why it feels meaningful. You care about your friends, your future, your next meal, Molecules don't, but those feelings are built on the same materials. Your ability to care comes from a nervous system, which comes from cells, which come from proteins, which came from something we're still trying to understand. Likely something warm, wet, and not particularly glamorous. In a universe filled with silence and repetition, life is noisy, disorganized, and constantly making more of itself. It's an unlikely exception to the general rule of nothing happens unless something forces it. But you, along with every other living thing, are proof that somehow that exception happened and kept happening. This leads us to consider the world you live in now, what life looks like from the outside, and why our daily experience of it might not tell the whole story. Look around you. Life is everywhere. It grows in gardens, hides in cupboards, buzzes past your ear, and sometimes turns up in your sandwiches uninvited. We're so used to it that we rarely stop to think about how peculiar it actually is. Living things do things that nothing else in the universe seems particularly interested in, like moving on purpose, reproducing, or turning lunch into thoughts. At first glance, life seems obvious. A cat is alive, a stone isn't, plants grow, metal rusts. We like clear categories, but biology doesn't always work that way. The difference between living and non-living isn't always as clear-cut as you might expect. Viruses, for instance, can reproduce, but only by hijacking living cells. Prions are infectious proteins with no DNA at all. Not exactly your typical houseplant. What all living things do share are a few basic traits. They grow, they respond to their surroundings, they use energy, and they reproduce. These are the signs we use to label something as alive. And yet each of these can be mimicked, up to a point, by things that aren't technically living. A fire, for example, consumes fuel and spreads. It reacts to its environment. But no one's suggesting it gets birthday parties. When we look closely, even the most complex life forms are made up of cells. Tiny, membrane-bound compartments filled with molecules. Cells take in raw materials, process energy, and get rid of waste. If this sounds familiar, that's because you're doing it right now, just at a much larger scale, and hopefully without leaking cytoplasm. The experience of life, as we see it day to day, can be misleading. It feels full of purpose, direction, and meaning. But the machinery underneath is unthinking and automatic. DNA is copied because it chemically fits. Proteins are built because molecules interact in specific ways. It looks coordinated, but there's no committee. It's just atoms following rules. What we see as purpose is really the result of processes that happen to persist. Living systems survive because they happen to work, not because they know what they're doing. There's no plan behind cell division. It just happens because the conditions make it happen. Your liver, for example, has been getting on with its job this whole time without once asking for recognition. This everyday experience of life can make it hard to imagine a time when none of this existed. When there were no cells, no metabolism, no replication. Just a planet full of chemicals waiting for the right accident. But that's where this story starts. Not with fully formed life, but with matter behaving exactly as it always has, and stumbling across something persistent. This leads us to consider the limits of human perception. Because to truly understand how life began, we'll need to shrink down, far, far smaller than anything we can see with our eyes. To understand how life began, we have to leave behind the world we can see. Life didn't start at the level of animals, plants, or even cells. It began somewhere far smaller, deep in the realm of molecules and atoms, where things behave differently. And most of it happens whether you notice or not, which, let's be honest, is probably for the best. The human eye can see things down to about the width of a human hair, roughly 70 micrometers. A single bacterium is already 10 times smaller than that. But the molecules responsible for starting life? They're thousands of times smaller still. We're talking about proteins, nucleotides, and amino acids. Tiny arrangements of atoms that float around, bounce into each other, and sometimes stick. Atoms themselves are mostly empty space. If the nucleus of an atom were the size of a pea, the outer edge of its electron cloud would be about 200 meters away. So when we say life started with a few atoms coming together, it's not as if they were queuing up shoulder to shoulder. They were more like vaguely interested strangers in a football stadium, occasionally bumping into each other and seeing what happened. Despite the scale, these particles obey consistent rules. The forces that bind atoms together, like covalent bonds and electrostatic attraction, work the same way whether you're in a puddle on early Earth or a laboratory in Cambridge. When conditions are right, certain atoms naturally form molecules, and some of those molecules behave in useful, repeatable ways. Chemistry, as it turns out, is stubbornly consistent. We can't directly see these reactions without special tools, but we can describe them. Molecules vibrate, rotate, and collide. Some break apart. Others rearrange into new structures. None of them have a goal. But sometimes, through sheer numbers and time, one molecule sticks around a little longer, or does something slightly more interesting than the rest. And eventually, that might matter. To help visualize the scale, imagine this. If a single cell were the size of a football stadium, a typical protein inside it would be the size of a paperclip somewhere on the pitch. And a single water molecule? Roughly the size of a speck of dust floating in the air above the stands. And yet, it's at this microscopic scale that life found its footing. It's also worth noting that these small-scale reactions are happening constantly. Right now, in your body, millions of molecular interactions are occurring every second, keeping you alive and making sure you stay mostly functional, which is arguably more than we can say for your internet connection. This leads us to consider how those reactions begin to form patterns. How simple chemistry lays the foundation for the first steps toward life. Now that we've shrunk ourselves down to the scale of atoms and molecules, it's time to see how simple chemistry might have kicked things off. Picture early Earth, about 4 billion years ago. Not a place you'd want to visit. The air was filled with gases like methane, ammonia, hydrogen, and water vapor. No oxygen, no ozone layer, and certainly no cafes. This chaotic mixture formed what scientists call a reducing atmosphere, a chemically reactive environment, lacking oxygen but rich in molecules that are eager to bond. Add in energy from lightning, volcanic heat, or ultraviolet radiation from the sun, and you've got the ideal setting for molecules to start rearranging themselves into more complex forms. Not through magic, just through basic chemical reactions. One famous experiment captured this idea. The Miller-Urey experiment in 1953. Two scientists simulated early Earth's conditions in a sealed glass flask. They added water, methane, ammonia, and hydrogen, then passed electric sparks through the mixture to mimic lightning. After just a few days, the flask was filled with brownish goo. More importantly, it contained amino acids, the basic building blocks of proteins. What this showed was simple. Given the right ingredients and energy, complex organic molecules can form naturally. No living cells were involved. No DNA, no enzymes, no direction. Just atoms reacting because they can. It wasn't life, but it was the kind of chemistry that life builds on, which is a bit like getting a set of random Lego bricks that, against all odds, start sticking together into something halfway useful. These small organic molecules, like amino acids, sugars, and fatty acids, are called prebiotic compounds. Prebiotic, meaning they came before life, but are the ingredients that life uses. The big question is, how do you go from a bunch of floating molecules to something that can grow, adapt, and make copies of itself? It turns out the chemistry doesn't stop at goo. Under the right conditions, some of these molecules can spontaneously link together. Amino acids can form chains called peptides. Sugars and nitrogenous bases can form nucleotides, the basic units of RNA and DNA. Lipid molecules can even arrange themselves into bubbles, creating primitive cell-like structures. None of it needs help. It just follows the rules of molecular interaction. And, while most combinations fall apart or do nothing, some stick around. Over time, some chemical systems can become stable, or even start influencing their own environment. That's the beginning of what we call self-organization. Again, no plans, no goals, just molecules trying things, most of which fail, occasionally followed by something that doesn't. This leads us to consider what happens when things don't fall apart. When molecules persist, repeat, and eventually start shaping their own future reactions. Once molecules started forming more complex structures, the next step wasn't instant life, but more chemistry, slower, messier, and still thoroughly unbothered by the idea of success. Some of these new molecules began doing things that looked suspiciously like progress, storing energy, holding shape, or influencing nearby reactions. Still no purpose, just more molecules reacting to conditions. Among these were nucleotides, small compounds made of a sugar, a phosphate group, and a nitrogen base. When they link together, they form long chains called RNA. RNA is interesting because it can do two jobs. It can carry information, like a blueprint, and it can also fold into shapes that help chemical reactions along. It's a bit like discovering your shopping list can also make dinner. Some scientists call this the RNA world hypothesis. The idea that before DNA and proteins, early life relied on RNA molecules to store and copy information, and maybe even catalyze basic reactions. These RNA molecules wouldn't have been perfect. In fact, they'd have made frequent errors, but some of those errors would have been useful. Others, less so, bit like most of our decisions really. Meanwhile, proteins, or at least their simpler precursors, may have been forming too. Proteins are long chains of amino acids that fold into very precise shapes. Those shapes determine their function, from carrying oxygen to breaking down sugars. In early Earth's oceans, some of these chains may have started to fold into forms that sped up reactions or stabilized other molecules. And then there were the bubbles, lipid molecules that naturally group together to form membranes. Under the right conditions, these lipids self-assemble into spheres, trapping bits of RNA or protein-like molecules inside. These primitive structures are called protocells. They're not alive, but they're a step in that direction. Tiny chemical compartments, doing chemistry, and occasionally surviving longer than the ones that fall apart. All of this was happening on a scale too small to see and too slow to notice. But over time, patterns began to emerge. Some chemical combinations lasted longer. Some copied themselves more effectively. Others used nearby resources faster than their rivals. Survival, in chemical terms, simply meant sticking around long enough to do it again. Crucially, there was still no design involved, no guiding force, just natural selection at the molecular level. The things that could persist did, the things that couldn't didn't. It's not glamorous, but it's surprisingly efficient. Nature's only requirement was, don't fall apart immediately. This leads us to consider how these simple systems scale up, not just across space, but across everything. From atoms to galaxies, the rules remain the same. The chemical processes that led to life on Earth might feel like a local oddity, but they aren't. The laws that allowed simple molecules to build complexity are not unique to our planet. They are part of the wider universe, predictable, repeatable, and entirely indifferent to what they produce. Life didn't happen because Earth was special. It happened because physics doesn't know how to stop. Across the galaxy, the same basic elements appear again and again. Carbon, hydrogen, nitrogen, oxygen. These atoms follow the same rules of bonding and interaction whether they're on Earth, floating in a comet's tail, or buried in the icy crust of a distant moon. Chemistry isn't regional. It doesn't care where it's happening, or who's watching, which, in most places, is no one. Astronomers have found amino acids, the building blocks of proteins, inside meteorites that have landed on Earth. Organic molecules have been spotted in interstellar gas clouds and on moons like Titan and Enceladus. These discoveries suggest that prebiotic chemistry isn't rare. It's probably going on all over the place. Life's ingredients seem to form naturally whenever the conditions are vaguely suitable. Of course, having the ingredients isn't the same as baking the cake. Life requires more than just molecules. It needs specific arrangements, energy sources, and enough time for reactions to repeat, mutate, and persist. But the fact that the raw materials are common means Earth's story might not be unique, just the one we happen to be in. What's remarkable is how consistent the rules are. Gravity curves space. Electrons repel each other. Molecules bond at specific angles and break apart when energy is applied. These physical laws don't take weekends off. Whether you're in a warm pond on early Earth or a hydrothermal vent on Europa, the same principles guide what's possible. This universality also highlights the indifference of nature. There's no suggestion that life was inevitable. It was simply allowed. The rules created an opportunity, not a destiny. That opportunity was taken, not because of any plan, but because molecules collided in just the right way, often enough, for just long enough. Hardly poetic, but reliably functional. The broader implication is this: life may not be rare because it's difficult, but because it takes time. A lot of it. And the universe is only just getting started. There could be countless places where life is trying, or failing, to get going, but wherever it does emerge, it will do so under the same rules that made us. Same chemistry, same physics, same odds, give or take a billion years. This leads us to consider how time itself factors in, and how the slow, quiet persistence of deep time gave those rules a chance to keep repeating until something stuck. If chemistry is the engine of life, time is the fuel. The processes that built the first living systems weren't fast or dramatic. They didn't arrive overnight. In fact, they unfolded so slowly over such vast timescales that if you blinked for a few million years, you'd probably miss the entire thing. Fortunately, molecules are famously patient. They've got nothing better to do. Earth is roughly 4.5 billion years old. The earliest signs of life, tiny fossilized microbial mats, appear in rocks that are at least 3.5 billion years old, maybe older. That means life started relatively early, geologically speaking. But early still means hundreds of millions of years of chemical fumbling before anything that could be called alive actually showed up. To grasp how long that is, imagine compressing all of Earth's history into a single 24-hour day. The planet forms at midnight. Life first appears around 4 a.m. Complex cells don't show up until 1:15 in the afternoon. Dinosaurs arrive at 10:56 p.m. Humans, somewhere in the last 4 seconds before midnight. And if that makes you feel slightly irrelevant, good. That's the appropriate response. This timescale is what makes improbable events not just possible, but likely. Given a big enough span of time, rare things happen. Chemical reactions repeat. Molecules assemble, fall apart, reassemble. The occasional success gets copied. Failure, conveniently, doesn't. The result is slow accumulation. Not because nature is clever, but because it doesn't give up. Deep time also explains how complex systems emerge from simple parts. It takes millions of years for a handful of stable molecules to become networks, for networks to become self-replicating, and for replication to start competing. There was no sudden leap, just a long, drawn-out process of molecules doing whatever the laws of physics allowed. Meanwhile, the planet was changing too. Volcanoes pumped out gases, oceans formed and evaporated, continents shifted, environments changed again and again, offering new conditions for chemical systems to try, fail, or adapt. Some theories suggest hydrothermal vents provided stable heat and chemical gradients. Others point to shallow pools exposed to sunlight. Whichever the setting, time gave each one a chance to work. What's striking is that life didn't arise at the peak of Earth's stability. It emerged during a time of chaos, meteor impacts, radiation, toxic gases, yet chemistry kept going. No matter how often it was interrupted, it started again. That's the advantage of deep time. It absorbs failures without blinking. This leads us to consider the nature of this persistence, not as a goal, but as the result of processes that, frankly, didn't care whether they succeeded or not. Nature doesn't root for anything. It doesn't pick favorites. It doesn't cheer when a molecule sticks, or frown when it falls apart. The emergence of life didn't require approval, design, or desire. It simply followed the laws of physics and chemistry over enough time for improbable things to become unavoidable. The universe did not care that it happened, and still doesn't. This indifference is key to understanding life's beginning. There was no moment where the universe suddenly decided to switch on biology. No narrator said, "Right, let's get this show going." Molecules formed, broke apart, and occasionally repeated. Systems that worked stuck around. Systems that didn't disappeared without ceremony. Life emerged not because it was meant to, but because nothing stopped it. In that sense, life is an outcome, not an aim. Chemistry produced a system that met the technical requirements for being alive, using energy, replicating, evolving. But there was no celebration when it crossed the line, no cosmic applause. It just continued, which, when you think about it, is really all life ever does. It continues until it doesn't. This can be unsettling. Humans like meaning. We like to think our existence is part of a plan. But nature doesn't deal in plans. It deals in probabilities and rules. The same laws that hold galaxies together also shape the molecules in your cells. If that feels a bit cold, fair enough. But it's also oddly reassuring. Life didn't need permission to begin. It just needed time and persistence. This perspective also helps explain why life is so adaptable. If it began through accident and survival, then of course it would be messy, diverse, and constantly changing. Life isn't one tidy formula. It's a spectrum of temporary solutions, all held together by molecules doing whatever they can to avoid breaking. The fact that it looks elegant from the outside is mostly coincidence. Even today, life continues in the same pattern. New species appear. Old ones go extinct. Cells divide. DNA mutates. The whole thing rolls on, driven not by intention but by underlying forces that don't know or care what they're driving. That might sound bleak, until you realize it also means there's no upper limit on what can emerge next. And through all this, the laws of nature remain unchanged. Whether applied to stars or swamp muck, atoms obey the same rules. There's no exception carved out for biology. Life is not a break in the system, it's a direct result of it. It's what happens when the laws are left to run long enough in the right conditions. This leads us to consider how human beings, eventually, began to notice this strange persistence and started asking what it all meant. Long before microscopes and lab coats, people were already observing life, just without knowing what they were really looking at. Early humans noticed the patterns around them: plants sprouting from soil, animals being born, seasons changing. To them, life seemed to come and go with rhythm, as if the world had a plan, even if that plan occasionally included floods, plagues, and the occasional angry sky god. With no understanding of atoms or molecules, these observations were interpreted through myth and storytelling. Life was often thought to be gifted by spirits, gods, or mysterious forces in the natural world. In many cultures, breath itself was linked to the soul, something invisible that entered at birth and left at death, which, in fairness, is a decent guess when you're working with zero data. Some of the earliest creation stories, Egyptian, Mesopotamian, Hindu, and others, described life emerging from water, clay, or chaos. While they weren't scientifically accurate, they reflected something important. People noticed that life tended to come from wet, warm, and fertile places, which, incidentally, is not far off from what some origin of life researchers now propose. Over time, these explanations became more elaborate. Civilizations like the Greeks, Chinese, and early Islamic scholars began cataloging plants, animals, and natural phenomena. A network error occurred. Please check your connection and try again. If this issue persists, please contact us through our help center at help@openai.com. Retry. Response. As humans started paying closer attention to the natural world, a shift began. From myth to observation, early civilizations often explained life's origins with stories involving gods, animals, and a lot of shouting from the sky. These stories offered meaning, but not much in the way of mechanism. It would take centuries before someone thought to ask, quietly, hang on, what's actually going on here? Some of the first steps came from ancient Greek thinkers, like Anaximander and Empedocles. They suggested that life might have arisen from water or mud, not divine will. Aristotle, for all his influence, got a bit carried away and proposed spontaneous generation, the idea that life could spring from non-living matter, like mice forming out of grain. A theory that, despite being incorrect, was weirdly popular for a very long time. The same pattern played out in other parts of the world. In early Indian philosophy, the idea of life arising from the elements, earth, water, fire, and air, was taken seriously. Ancient Chinese texts explored the concept of Kai as a life force. These were early frameworks, not based on testable evidence, but rooted in close observation and genuine curiosity. You could say they were making do without microscopes. It wasn't until the 17th and 18th centuries that things began to shift from speculation to something resembling science. Antony van Leeuwenhoek, using handcrafted lenses, discovered microscopic animalcules in pond water, tiny living creatures previously invisible. Suddenly, there was a whole new level of life to consider, and it wasn't made of mud or divine breath, it was made of cells. In the 19th century, Louis Pasteur dealt a final blow to the idea of spontaneous generation by showing that microbes only appeared in broth if the broth was exposed to air containing them. Life didn't just appear, it came from existing life. A reassuring result for soup lovers everywhere. At the same time, Charles Darwin was quietly redefining how we think about change and complexity. His theory of natural selection didn't focus on life's origin directly, but it gave a framework for how living systems could change and adapt without guidance. Once life began, it didn't need planning. It just needed time and variation. These early insights didn't hand us the answer, but they narrowed the field. By observing, experimenting, and questioning their own assumptions, early scientists began clearing away the myths. What remained was the realization that life is built from simpler parts, and those parts might not be alive at all. This leads us to consider how our growing curiosity and our rather nosy habit of building tools allowed us to look even closer at life's hidden layers. As questions about life's origins became more precise, our tools had to improve too. You can't solve molecular puzzles with your eyes alone. Not unless you've got unusually detailed vision and a very patient lab partner. Luckily, human curiosity comes with opposable thumbs, and we've spent centuries building instruments to see what nature doesn't make obvious. Microscopes were a turning point. What began as a stack of curved glass eventually revealed entire hidden worlds. In the 17th century, van Leeuwenhoek's simple lenses showed tiny, moving organisms in water. Later, compound microscopes exposed the structures within cells, nuclei, membranes, and eventually, organelles. It turned out life wasn't one thing. It was a crowded community of cooperating parts. But seeing life is one thing. Understanding it means taking it apart. The rise of chemistry brought methods to isolate and analyze those parts. Scientists developed techniques like chromatography to separate mixtures and spectroscopy to identify molecules by how they absorb light. Biochemistry emerged as a field in its own right, blending biology with chemistry to study the machinery inside cells. One of the biggest breakthroughs came with X-ray crystallography. This technique allowed researchers to determine the shapes of biological molecules by analyzing how X-rays scattered through crystals. It was how Rosalind Franklin captured the famous images that helped reveal the double helix structure of DNA, arguably the most famous spiral that isn't part of a staircase. Later came electron microscopes, offering magnification thousands of times stronger than light microscopes. Suddenly, scientists could see viruses, ribosomes, and even the structure of large protein complexes. Today, we use tools like cryo-electron microscopy to freeze molecules mid-action, revealing how they twist, bond, and break apart, often in processes that life depends on to function. Modern computing has expanded our methods further. We can simulate chemical reactions digitally, modeling how molecules behave over time without ever stepping into a lab. Databases store entire genomes. Algorithms predict protein shapes. It's not quite downloading life, but we're edging dangerously close to having to install updates. All these tools have one thing in common. They've helped us move from guesses to measurements, from wondering what life is to understanding what it's made of. And crucially, they allow us to test our theories. If life started with certain chemicals under specific conditions, we can now recreate those scenarios and see what actually happens. This leads us to consider what we've got wrong along the way, and how science handles being, well, completely mistaken. Scientific progress rarely moves in a straight line. More often, it zigzags between, "that sounds reasonable," and, "oh, that was completely wrong." The study of life's origins has been no exception. For every clever theory, there's usually a pile of discarded ideas behind it, many of which were taken very seriously at the time. Some still are, though mostly by people who stopped reading in 1850. One of the longest-running errors was spontaneous generation, the belief that life could arise directly from non-living matter, instantly and repeatedly. People thought maggots came from meat, frogs from mud, and mice from sacks of grain. To be fair, they didn't have germ theory, and nature does tend to be vague about her methods. Still, the theory held on for centuries before being disproven. Louis Pasteur finally closed the lid, literally, on the idea. His experiment with sterilized broth showed that if you kept airborne microbes out, nothing grew. Life didn't appear unless life was already there. This was a breakthrough, but it raised a new problem. If life can't appear from nothing today, how did it ever appear at all? Later misunderstandings were subtler. In the early 20th century, scientists believed proteins were the carriers of genetic information simply because they were more chemically complex than DNA. DNA was considered too boring, just a repetitive molecule with 4 bases. That is, until Watson, Crick, and Franklin showed how its structure made it perfect for storing and copying information, awkward for protein enthusiasts. Even today, ideas about the origin of life are revised as new data comes in. Early theories focused heavily on the primordial soup, a warm pond full of organic molecules. Later research suggested life may have begun near hydrothermal vents on the ocean floor, where energy and chemicals flow constantly. Neither idea has been disproven, but they've both needed adjustment as we've learned more. That's how science works. You propose an idea, test it, realize it's wrong or incomplete, and try again. It's less like a smooth staircase and more like falling up a rocky hill with occasional bursts of insight. Frustrating, yes, but also honest. It takes a particular kind of confidence to say, "we don't know yet," and then keep going anyway. The beauty of scientific error is that it tends to be temporary. Each mistake, once spotted, helps clear the way forward. Over time, ideas are refined, replaced, or quietly retired. It's a long game of narrowing the unknown, guided by evidence rather than instinct. Though occasionally instinct still tries to have a go, bless it. This leads us to consider how we've tried to untangle the problem more directly, through carefully planned experiments that test not what seems right, but what actually holds up. By the 20th century, it became clear that asking how life began couldn't rely on guesswork or poetic metaphors. We needed to test things, which meant building experiments, controlling conditions, and patiently waiting for results. Not always glamorous, but essential if you want to go from interesting theory to repeatable outcome. And yes, that often meant watching test tubes for weeks. One of the most famous experiments remains the Miller-Urey experiment of 1953. Stanley Miller and Harold Urey recreated what they thought early Earth's atmosphere looked like: water vapor, methane, ammonia, and hydrogen, and added electric sparks to simulate lightning. After a few days, the liquid turned brown and, more importantly, was full of amino acids. It wasn't life, but it was chemistry heading in the right direction. Since then, variations on that experiment have produced sugars, fatty acids, and even nucleotides. What these studies show is that complex organic molecules can form under a range of natural conditions: different gases, different energy sources, sunlight, volcanic heat, shock waves. All roads seem to lead to goo. Slightly unpleasant goo, but chemically promising nonetheless. Other experiments focused on what happens after those building blocks appear. Could they link up to form polymers, long chains like proteins or RNA? Under certain conditions, yes. For example, when amino acids are dried and heated, they start forming short chains. On mineral surfaces like clay, molecules can align and connect more easily. Turns out life's first attempts may have involved a lot of mud. To test how primitive molecules might replicate, researchers have built simple RNA strands in the lab that can copy parts of themselves. These molecules are clumsy and error-prone, more DIY enthusiast than factory robot. But they do demonstrate a key idea. Replication doesn't need to be perfect. It just needs to work most of the time, which is frankly a good summary of biology in general. Experiments have also created protocells, tiny bubbles made from lipids that resemble primitive cell membranes. Drop them into water and they spontaneously form spherical containers. Some can even grow or divide. It's not quite life, but it's close enough to raise eyebrows. If molecules can gather, protect themselves, and react with their surroundings, that's a strong nudge in the right direction. Crucially, these experiments are repeatable. They don't rely on miracles. They work not because we cheat the conditions, but because we replicate the environments that may have existed billions of years ago. In other words, nature doesn't need help. It just needs time, ingredients, and the occasional lightning bolt. This leads us to consider how science, as a whole, doesn't happen in isolation. These breakthroughs were rarely solo efforts. They came from a collective, slow-burning collaboration across generations and continents. The search for life's origins hasn't been a one-person job. It's taken thousands of researchers across decades and continents, quietly building on each other's work. No dramatic eureka moments, just experiments, lab notes, arguments, corrections, and the occasional paper that makes everyone go, "Wait, what?" Scientific discovery, especially in this field, is more relay race than solo sprint. Take Alexander Oparin in the 1920s. A Russian biochemist, he proposed that life began as a gradual chemical evolution. Molecules in Earth's early atmosphere forming a soup of increasingly complex compounds. Around the same time, British scientist J.B.S. Haldane suggested a similar idea independently. Different labs, different countries, same train of thought. As if life's origin was just waiting to be rediscovered. Later, researchers like Sidney Fox explored how heating amino acids could spontaneously form protein-like chains. Leslie Orgel worked on how RNA might have copied itself. Jack Szostak showed how simple molecules could form protocells in the lab. None of these scientists solved the mystery, but each brought a piece of the puzzle. Science, it turns out, is full of people picking up where others got stuck. This collaboration stretches across disciplines too. Biologists work with chemists. Geologists chime in with details about early Earth conditions. Even astronomers join the conversation, because knowing where Earth got its elements means understanding the wider universe. It's like planning a group project with everyone, except some of them lived 300 years ago and never met. The flow of information hasn't always been smooth. Scientists don't always agree on the right approach. Some argue RNA came first, others back metabolism first theories. Still others propose lipids played the starring role. The debates can be frustrating, but they're part of the process. Each disagreement is a chance to test, refine, and rethink assumptions. As usual, progress comes wrapped in polite disagreement and, occasionally, pointed footnotes. Importantly, this global effort reflects the way science actually works. It's not just a set of facts, it's a way of asking questions that survive changing opinions. When new data arrives, theories shift. When old ideas are disproven, they're replaced. Not with bitterness, but usually with a quiet sigh and a new grant proposal. Progress is slow, but surprisingly reliable. This international, intergenerational project shows how science builds knowledge brick by brick. No one person can take credit. And that's the point. The search for life's origin is too big, too complex, and too uncertain for any one lab coat to solve alone. It demands patience, humility, and more than a little collective stubbornness. This leads us to consider what that stubbornness has brought us. How today's tools let us look deeper, measure finer, and get closer than ever before to answering the question. Today, scientists studying the origin of life have tools that would have seemed like science fiction just a century ago. We can peer into molecules, simulate the early Earth, and even build synthetic versions of life's parts. Precision has replaced speculation, though to be clear, there's still plenty we don't know. But now, when we're wrong, we can at least be wrong in high definition. Take molecular biology. With modern sequencing technology, we can read genetic codes base by base, billions of letters long, across countless organisms. This has revealed deep similarities between all known life. Whether it's a bacterium or a blue whale, the underlying code is written in the same chemical language. That's a strong hint that everything living today shares a common ancestor. We also have techniques like mass spectrometry, which can identify molecules based on their weight and structure, and high-resolution imaging, like cryo-electron microscopy, which can show proteins frozen in motion. These methods let scientists study reactions that happen in milliseconds, hardly enough time to boil a kettle, but long enough to build a cell. In origin of life research specifically, labs can now recreate more realistic environments. Rather than just zapping gases in a glass flask, researchers simulate hydrothermal vents, freezing cycles, tidal zones, or mineral surfaces. These experiments test how molecules behave under actual early Earth conditions, not just what's possible, but what's probable. We've also entered the age of synthetic biology. Scientists can now design artificial cells, create new strands of DNA, and even build RNA molecules that can copy themselves in the lab. None of this is conscious or alive in the full sense, but it shows how close chemistry can get to life's boundary without tipping over it. It's like constructing a door frame and watching to see if something tries to walk through. Computational tools have added even more precision. With advanced modeling software, researchers can simulate molecular interactions too complex to observe directly. Supercomputers run chemical scenarios over and over, testing combinations, conditions, and outcomes. This doesn't replace real-world data, but it speeds up the work dramatically, especially when you're dealing with reactions that take weeks to repeat in a lab. Of course, precision doesn't mean perfection. The more detail we uncover, the more complexity we find. The puzzle isn't finished, it's just better lit. There's no single experiment that has solved the origin of life. But modern tools have given us clearer boundaries, sharper questions, and far fewer excuses for fuzzy thinking. This leads us to consider what we're still missing. Because even with all these advances, many of the deepest questions remain wide open. Despite all the progress, several major questions about life's origins remain unanswered. Some of these gaps are practical. We simply can't yet recreate the full journey from raw molecules to living cells. Others are more conceptual. We're still debating what we even mean by life, which, given how much we talk about it, feels slightly embarrassing. One challenge is the first step. Where did the key building blocks come from? We know amino acids and sugars can form under the right conditions, but we don't know how likely that was on early Earth. Did they form in the atmosphere, in volcanic pools, deep in the ocean, or arrive on asteroids? It's a bit like guessing where someone grew up based only on their accent, and they refuse to tell you. Then there's the RNA problem. Many researchers support the RNA world hypothesis, that RNA came before both DNA and proteins, because it can both store information and catalyze reactions. But even in the best lab conditions, making RNA from scratch is tricky. The individual components, nucleotides, are finicky to form and join up. It's like trying to build a Lego set when half the pieces keep dissolving. Another mystery is how chemical systems became self-sustaining. Metabolism-first theories suggest that chemical cycles, powered by natural energy sources, laid the groundwork. But these ideas often require very specific conditions, and, unfortunately, we don't have access to a time machine to check whether ancient hydrothermal vents were cooperating. We also don't fully understand how protocells transitioned into true cells. We can make lipid spheres in the lab that can hold RNA or basic reactions. But real cells have membranes that regulate what goes in and out, and internal systems that control growth and division. At some point, chemistry crossed into biology. That crossing remains hazy. And then there's the biggest unknown of all. How likely is this process? Was life on Earth the result of rare conditions coming together just once? Or does chemistry naturally head in this direction whenever planets are wet and warm for long enough? We'd love a second example. Life elsewhere. But so far, Earth is all we've got. Uncertainty isn't failure, though. It's just part of the job. In fact, the more we learn, the better we understand what we don't know. And in origin of life research, that's actually progress. Each blank spot tells scientists where to focus next. There's no shame in saying we don't know, as long as you follow it with yet. This leads us to consider what we might find if we look beyond Earth. Because if life began here, perhaps it's begun elsewhere too. If life emerged on Earth, could it have emerged elsewhere? It's one of the simplest questions, and one of the hardest to answer. The ingredients for life, carbon, water, energy, are common across the galaxy. But ingredients alone don't guarantee a cake, especially not one that divides, evolves, and occasionally writes passive-aggressive tweets. Let's start close to home. Mars once had lakes, rivers, and a thicker atmosphere. It was warm and wet for hundreds of millions of years, conditions not unlike early Earth. A network error occurred. Please check your connection and try again. If this issue persists, please contact us through our help center at help@openai.com. Retry. Response. If life began here, the natural question is, has it begun anywhere else? For scientists, that's not just idle curiosity. It's a way to test whether life is a freak occurrence or a regular feature of certain kinds of planets. Unfortunately, so far, the universe has been about as communicative as a teenager asked how their day was. Still, we do have a few good places to look. Mars, for one, was once warmer, wetter, and possibly much more habitable. Its surface today is bone-dry and freezing, but evidence from rovers suggests it once had rivers, lakes, and possibly oceans. If life ever got started there, some traces might still linger underground, or at least fossilized, somewhere beneath all the dust. Even more promising are the icy moons of the outer solar system. Europa, orbiting Jupiter, and Enceladus, orbiting Saturn, both have subsurface oceans beneath their frozen crusts. These oceans are kept warm by gravitational flexing. Not exactly central heating, but it works. And they seem to have the three key ingredients for life: liquid water, organic compounds, and energy. Enceladus even sprays its ocean into space via geysers, saving us the trouble of drilling through kilometers of ice. The Cassini probe flew through one of those plumes and detected salts, organics, and small molecules like hydrogen. That's not life, of course, but it is what life could use. Like finding flour, sugar, and eggs scattered near an oven. No cake yet, but the kitchen's open. Further afield, astronomers are discovering planets orbiting other stars. Thousands of them. Some lie in the so-called habitable zone, where liquid water might exist. Others are gas giants with moons that, like Europa or Enceladus, could have internal oceans. We can't visit these worlds yet, but we can study their atmospheres. A mix of gases like oxygen and methane, out of balance, might hint at biology. This search is known as astrobiology, a field combining chemistry, geology, astronomy, and, frankly, wishful thinking. The trouble is, without a second example of life, we don't yet know what we're looking for. It's like hunting for aliens with a very detailed picture of a duck and hoping something quacks back. Still, the search continues. Missions like the James Webb Space Telescope, the upcoming Europa Clipper, and the Perseverance rover are all part of the broader effort. Each one might help us find signs of life, or, at the very least, rule out places where it definitely isn't. This leads us to consider one final possibility. If we never find life elsewhere, does that make Earth unique, or just unlucky in the galactic neighbor department? If we never find life beyond Earth, one possibility is that it simply isn't there. Not because the universe is lifeless by nature, but because the chain of events that led to life here was so specific, so local, that it might not have happened anywhere else. A one-off experiment in a very large, very quiet laboratory. This idea isn't particularly popular, not because it's wrong, but because it's lonely. Scientists call it the rare Earth hypothesis. It suggests that while simple planets may be common, the combination of traits that made Earth hospitable to life, liquid water, plate tectonics, a stable climate, a protective magnetic field, and just the right mix of elements, might be vanishingly rare. Like winning the lottery, then being struck by lightning, then meeting someone who enjoys small talk at bus stops. There's also the matter of timing. The universe is 13.8 billion years old, but complex life only showed up on Earth in the last half billion. If life needs several billion years of stability to develop, then maybe most planets just don't have that kind of patience. Stars explode. Orbits wobble. Asteroids, as dinosaurs discovered, don't send warnings. Still, being alone wouldn't mean being unimportant. Quite the opposite. If life on Earth is the only example, it would make our planet the single known refuge of biology in the entire observable universe. Not one of many, but the only one. A rather high-stakes position for a rock that's mostly covered in water and occasionally sets bits of itself on fire. And if we are the only ones here, then all the beauty and complexity of biology, cells, brains, ecosystems, narwhals, exists in just one place. Every leaf, every microbe, every awkward human conversation would be a rare artifact in a universe otherwise filled with sterile chemistry. This view comes with responsibility. If Earth is unique, then the continued survival of life depends on us. Not in a heroic chosen one way, more in a slightly uncomfortable custodian of the last surviving houseplant way. We can't assume someone else out there will figure it out. Of course, the absence of evidence isn't evidence of absence. We haven't looked everywhere. We've barely looked anywhere. But it's worth thinking about what it would mean if we searched and never found anything looking back. This leads us to consider a final question. If we're not alone, why is everything else so quiet? If the universe is teeming with planets, and we suspect that life might be fairly common, then where is everybody? This is known as the Fermi paradox, the apparent contradiction between the high probability of extraterrestrial life and the complete lack of any evidence for it. You'd think at least one alien civilization would have dropped by for tea or accidentally left a receipt. To be clear, we've been listening. Radio telescopes have scanned the skies for decades, searching for artificial signals. Something structured, repeated, or just weird enough to be unnatural. So far, nothing. A few intriguing blips have popped up, like the "wow" signal in 1977, but they've never repeated. It's hard to build a theory on one anonymous voicemail. There are several possible explanations. One is that intelligent life is very rare. Civilizations may arise, but then quickly disappear due to self-destruction, environmental collapse, or simply bad luck. In this view, intelligence might be less a survival advantage and more a cosmic health hazard, like giving a toddler a box of matches and a nuclear reactor. Another possibility is that alien life is out there, but it's just not talking. Perhaps advanced civilizations avoid broadcasting for fear of being noticed, or they communicate in ways we can't detect, using technologies beyond our imagination, or simply not using radio at all. We may be listening for shouts when everyone else is whispering in ultrasonic. Then there's the zoo hypothesis, which suggests that we're being deliberately avoided or observed. like animals in a nature reserve. It's not the most flattering idea, the alien equivalent of "don't poke the primitive species." They're still throwing elections. But as with most of these explanations, there's no evidence either way. A more mundane explanation is that space is just very big and very slow. The galaxy is 100,000 light years across. Even if civilizations are common, they may be too far apart to ever detect each other. Light takes time to travel. Messages might still be on the way, or long forgotten by the time they arrive. It's also possible we're looking too early. Human technology has only been around for a cosmic blink of an eye. Our radio signals have traveled just over 100 light years, a tiny bubble in one corner of one galaxy. The odds of another civilization being in range, at the right time, and listening, not great. Still, the silence matters. If it continues, we'll need to rethink our assumptions. Not just about aliens, but about ourselves. Maybe it's temporary, or maybe it isn't the main story at all. Just a brief footnote in a universe mostly governed by hydrogen and gravity. This leads us to consider the final question. Whatever life is, why does it seem to be the exception, not the rule? So far, life seems to be the anomaly. In all our searching, all our telescopes and calculations, and cautious optimism, we've yet to find anything else quite like it. Despite the size of the universe and the number of planets, biology still looks suspiciously like a local phenomenon, which is either deeply profound or deeply annoying. It's not for lack of trying. We've sent spacecraft to every major planet in our solar system, peered into exoplanet atmospheres, and monitored signals across the electromagnetic spectrum. And what have we found? A lot of chemistry. Interesting chemistry sometimes, but chemistry nonetheless. No microbes, no algae, no polite alien civilizations asking to borrow a cup of sugar. This might suggest that life is less like a crack in the pavement and more like a rare mineral, one that only forms under the most specific of circumstances. Water helps, certainly. So do the right temperatures, elements, and a bit of geological time. But clearly, those ingredients alone aren't enough. Earth has some extra quality that so far we can't quite pin down. One idea is that the origin of life is an extremely improbable event. A series of steps, chemical, structural, and energetic, that must occur in just the right sequence. If any part of that sequence is missing, nothing happens. The universe might be full of half-started experiments, warm ponds with no spark, oceans with no replication, planets full of potential that just never got going. Then there's the possibility that life is easy to start, but hard to sustain. Maybe microbes are out there, thriving under rocks on distant moons, or hiding in Martian soil. But complex life, animals, ecosystems, societies, might require a rarer set of conditions, like a very specific recipe, but you have to cook it blindfolded, underwater, while being occasionally hit with comets. It's also worth asking whether we're even looking for the right thing. All life on Earth is based on DNA, carbon, and water. But could other forms exist? Life made of silicon, or using ammonia instead of water? Possibly. But it's hard to recognize life when you're not sure what you're looking at. Like trying to find a needle in a haystack when you've never seen a needle, and the hay keeps setting off false positives. Still, even if we're the exception, that doesn't make us insignificant. If anything, it makes Earth even more extraordinary. A speck of biology in a sea of physics, a place where atoms started doing something odd and kept at it for 4 billion years. This leads us to consider the final question of the evening. What does all this say about us? And what do we do with the answer? If life really is rare, then Earth may be an outlier. Not just special, but statistically bizarre. The rare Earth hypothesis suggests that complex life depends on such a strange combination of conditions that it may hardly ever happen. It's not enough to have a planet in the right zone. You need all the weird extras too. For starters, we have plate tectonics. This constant recycling of the crust regulates carbon dioxide, keeping temperatures within reasonable limits. It's a bit like the planet has central heating, only the system runs on molten rock and occasional volcanic outbursts. Many planets don't have this, which might explain why they're frozen, scorched, or both, depending on the mood. Then there's our unusually stable climate over geological time. Yes, there have been extinctions and ice ages, but life has always bounced back. That's partly thanks to Earth's magnetic field, which protects the atmosphere from being stripped away by solar winds. Without it, we'd probably look like Mars, minus the Instagram filters. Another factor is our large moon. It stabilizes the planet's axial tilt, which helps keep the seasons predictable. No wild swings from tropical rainforest to frozen tundra every few millennia. The moon also causes tides, which may have helped early life transition from sea to land. Not bad for a giant space rock formed by a catastrophic collision. And then there's Jupiter. It acts as a kind of cosmic bouncer, deflecting or swallowing many of the comets and asteroids that could otherwise have smashed into Earth. Though clearly it doesn't catch all of them, as the dinosaurs would probably point out, if they still had a complaints department. Put all this together, and Earth starts to look like the result of multiple rare coincidences stacking up. Perhaps microbial life is fairly common, but complex ecosystems, intelligence, civilization, those might only emerge once in a galaxy. Or less. Which would mean we're not just unusual, we're borderline absurd. Of course, this is still a hypothesis. We've only got one sample planet to study. The more we learn about exoplanets, the more we might discover that some of these features aren't as rare as they seem. But so far, Earth still holds the record for biodiversity, geology, and the ability to generate YouTube comments at scale. So, if the rare Earth idea is right, then life like ours isn't just unlikely, it's precious. Not because it's superior, but because it's fragile, temporary, and hard to repeat. Which raises a final question. If we're truly alone, or nearly so, what responsibility does that place on us? If Earth really is that rare, and if life, especially intelligent life, is even rarer, then it puts rather a lot of weight on what we choose to do with it. We're not just one species on one planet. We might be the only species in the observable universe currently aware it exists. No pressure then. It's a strange position to be in. On the one hand, we're just hairless apes with Wi-Fi. On the other, we're capable of physics, poetry, surgery, and trying to understand what dark matter is, even if it currently refuses to cooperate. Somehow, atoms got together, made cells, and eventually started worrying about climate change and whether anyone actually likes coriander. This doesn't make us superior, just extraordinarily lucky. We've inherited a planet that's warm, wet, and chemically experimental, and then added cities, satellites, and the concept of irony. In cosmic terms, that's quite a leap. Not because it was inevitable, but because it could so easily not have happened. We often frame things in human-centered terms: progress, achievement, control, but zoom out a bit, and it's clear how fragile it all is. A thin atmosphere, a wobbling orbit, a few degrees of warming, and the whole experiment could slide backwards rather quickly. Evolution doesn't hand out refunds. That's why perspective matters. It's not about making us feel small or large. It's about realizing we're temporary custodians of something wildly improbable. The only planet, so far, that makes forests, whales, barbecues, and Bach. Not bad, as inventories go. Shame about the plastic. Of course, the universe will continue without us. Stars will burn, galaxies will collide. Physics doesn't care about Shakespeare. But caring is our thing. We notice beauty, we ask questions, we try badly to look after each other, which is rare and therefore worth preserving. So tonight isn't just about science, it's about the quiet shock of being here at all. Life on Earth didn't have to exist. Complex life didn't have to evolve. Civilization didn't have to build telescopes and ask if anyone else is out there. But here we are, asking anyway. Which leads us to the final reflection, not where we are, but what we choose to do. Now that we know how unlikely we are, we end where all stories of life eventually do, with responsibility. If we're the only spark of consciousness in this galaxy, or even just one of very few, then everything we build, protect, or destroy carries more weight than we might have imagined. This isn't just our home, it could be the only one where anything wonders what stars are. For a long time, we treated the planet as infinite. Infinite forests, infinite oceans, infinite atmosphere. Turns out none of that is true. What's remarkable isn't how much we've changed Earth, it's how quickly we've done it. In a geological blink, we've altered climate, ecosystems, and the chemistry of the air itself, mostly by accident, while arguing about whose turn it was to do the recycling. We now live in what many call the Anthropocene, a time when human activity is the dominant force shaping the planet. Not in some triumphant way. More in the sense of accidentally sitting on a priceless vase, then claiming it was already cracked. We're clever, but we're not great at foresight. Yet despite our tendency to leave things late, we've begun to understand our impact. We know the physics of climate change, the limits of biodiversity, the fragility of the systems that keep us fed and watered. We also know that action is still possible. The challenge is less about invention and more about motivation. The Earth doesn't need us. It's been through far worse. Mass extinctions, asteroid strikes, the entire Permian period. Life usually finds a way back, but we might not be part of that recovery. We're clever, yes, but not asteroid-proof. And evolution isn't sentimental. If we mess it up, the planet will eventually reboot. So perhaps the real task isn't just survival, it's stewardship. Not conquering nature, but living with it. Managing a delicate balance between human progress and planetary health. Which, let's be honest, is a tougher sell than unlimited bacon or free streaming, but far more necessary. We're the only species we know of that can study galaxies, write poetry, build particle accelerators, and accidentally invent deep-fried cheese. It would be a shame to throw all that away, especially when we've come this far from stardust to sushi. If we value intelligence, we ought to act like it occasionally. And so, tonight, as we look out at the stars and wonder who else might be watching back, it's worth remembering that the rarest thing isn't life. It's life that knows it's rare and tries to carry on anyway. Meanwhile, across the vast emptiness between stars, the universe remains mostly silent, not in a poetic way, but in a very literal very radio static sort of way. For all our listening, watching, and hopeful signaling, we've yet to hear so much as a cosmic hello, which either means nobody's out there or everyone's ignoring us. Both slightly awkward. This is often referred to as the Fermi paradox. If the universe is big, old, and full of stars with planets, then intelligent life should be common. Civilizations should be buzzing about. And yet, nothing. No signals. No Dyson spheres. There are, of course, plenty of possible explanations. Perhaps intelligent life is rare, or short-lived, or tends to self-destruct before developing interstellar Wi-Fi. Maybe we're listening on the wrong frequencies, or looking in the wrong ways. Maybe it's us who are weird for expecting a universe full of chatty aliens. Or perhaps the universe is simply quiet because it's early. Not by human standards, obviously. We've barely mastered toast without burning it, but on cosmic timescales. Perhaps we're among the first, the pioneers. Which sounds noble, until you realize it's also quite lonely, and there's no guarantee anyone turns up later. Another possibility is that advanced civilizations go quiet on purpose. A sort of galactic, do not disturb policy. Maybe broadcasting your presence attracts the wrong sort of attention. Or maybe they've all moved on to simulated realities and can't be bothered with the physical universe anymore. Bit like us and email spam filters. But perhaps the silence says something else entirely. Maybe it's not about them, it's about us. Maybe we're not ready to listen properly, not just technologically, but culturally. Still too focused on arguing over parking spaces and whether pineapple belongs on pizza. Which, to be clear, it absolutely does not. And so, we keep searching. Not out of desperation, but curiosity. Because even if the answer is that we are alone, or at least temporarily alone, it still tells us something vital. It tells us that life is not guaranteed, that awareness is not widespread, and that existence, even at its quietest, is still worth paying attention to. This leads us to consider something subtler, not just what we're waiting to hear, but what we might choose to say first. This leads us to consider something surprisingly tricky. If someone out there really is listening, what exactly would we say? For all the effort we've put into building telescopes and radio dishes, our message to the cosmos is, well, a bit of a muddle, a mix of maths, music, and, bizarrely, drawings of naked humans, hardly the galaxy's greatest hits. The idea behind most messages is simple. Start with universal basics. Mathematics, physics, things that should be the same everywhere, assuming aliens also enjoy algebra. From there, you can build up to more complex ideas, like what we look like, how our DNA works, and ideally, why we're not all terrible all of the time. One of the earliest attempts was the Arecibo message in 1974, just 1,679 binary digits, arranged in a grid, carefully designed to say, "Hello, we're here." And we like prime numbers. It was sent toward a globular cluster 25,000 light-years away, which means the soonest we'd hear back is roughly 50,000 years. Good luck putting that in your calendar. Other messages have been attached to spacecraft. The Voyager probes, launched in the late 1970s, each carry a golden record containing music, greetings in dozens of languages, and even the sound of a kiss, which is either very sweet or very awkward, depending on how you feel about aliens listening to 70s Earth smooches. Then there's the question of tone. Do we sound proud or apologetic, optimistic or cautious? So far, our messages tend to be hopeful, but perhaps a little too confident, as if saying, "Look at us. We built pyramids and invented jazz," whilst quietly ignoring the bits where we've also built nuclear weapons and reality television. It also raises the issue of who decides what to say. A message from humanity suggests we're speaking as one, which, if you've ever read the internet, seems wildly optimistic. We can barely agree on where to put the milk in tea, let alone craft a unified statement to other civilizations. Still, the act of trying matters. Even if no one ever hears us, the process forces us to think about who we are, what we value, what we'd want others to know. It's like writing your own biography and realizing most of it is about toast and traffic. But at least you're being honest. So far, the universe hasn't replied. No messages, no probes, no interstellar mixtapes. But the silence doesn't stop the question. If someone answered tomorrow, would we be ready to respond? So far, we've assumed that if aliens sent us a message, we'd understand it. But this leads us to a rather uncomfortable possibility. What if they already have, and we simply didn't recognize it? The universe may be humming with signals, but if we're not tuned in properly, they might as well be whispers in a hurricane. Most of our efforts rely on familiar methods: radio waves, laser pulses, the occasional mathematical pattern, all based on what we know and use. But that's the catch. Aliens, if they exist, may not think like us. Their technology might not resemble ours at all. It's a bit like expecting a whale to knock using Morse code, in the dark, underwater. While also being a whale, even defining what counts as a message is tricky. A signal might not be a signal. It could be something we dismiss as noise, or background radiation, or an oddly shaped galaxy that's actually a slow-motion billboard. The truth is, we're not entirely sure what we're looking for. We just hope we'll recognize it when it arrives. There's also the possibility of information being embedded in things we haven't considered. Maybe they've encoded messages in particles, or gravity waves, or even the cosmic microwave background. All clever places to hide a postcard, although slightly more difficult to read than your average birthday card. To complicate matters further, even if we detected something unmistakably artificial, say, a repeated burst with a prime number sequence, it might still take decades to decode. Assuming we ever do, it's a bit like finding an alien USB stick with no idea where to plug it in, and no instructions, because of course there wouldn't be. Human languages are already tricky enough. Ask anyone who's tried to learn Icelandic after a long day. Now imagine trying to understand a civilization that evolved on another world, with different senses, logic systems, and probably an opinion about oxygen that's politely baffled. Communication might require not just translation, but rethinking what language even is, which is why many scientists focus on universal principles: maths, physics, the structure of atoms. But even then, interpretations can vary. What we think of as a clear signal could, to someone else, resemble an accidental sneeze from a pulsar. So much depends on context, and we have very little of it. This leads us to consider another possibility. If aliens are out there, and if they've sent a message, then maybe the real question isn't, have they spoken? But are we ready to listen? This leads us to one of the more uncomfortable questions in all of SETI. Are we absolutely sure we want anyone to reply? Up to now, we've mostly assumed that aliens, if they exist, are friendly, wise, and possibly very good at chess. But there's no law that says they have to be nice. The universe isn't exactly known for its sentimentality. Some scientists argue that actively sending messages into space, what's called active SETI, might be a bit reckless. After all, if you're not sure who's out there, broadcasting your location seems a bit like shouting your address into the woods and hoping the bears aren't hungry. It's optimistic, but also quite possibly daft. This isn't just wild speculation. In evolutionary terms, intelligence doesn't necessarily mean kindness. On Earth, the smartest animals are usually quite competitive. Dolphins bully each other. Chimps form alliances and backstab like Shakespearean villains. And humans, well, we've got history, don't we? Then again, it's possible that any civilization advanced enough to cross interstellar space has already survived its own self-destructive phase. Maybe cooperation becomes essential at that scale. Or maybe they've just run out of planets to conquer and decided to try gardening. It's hard to say when you've never met one. Stephen Hawking, not known for alarmism, warned that making contact could go badly. His comparison? Native peoples meeting European explorers. That didn't exactly end in hugs and shared technology. Of course, others argue that any civilization able to receive our signals has probably already noticed us, thanks to decades of TV leaks and radar noise. Which means the cat's already out of the interstellar bag. There's also the philosophical view that curiosity is worth the risk. After all, if every species kept to itself out of fear, the galaxy would be a very quiet place indeed. Some argue that reaching out is part of growing up as a civilization. Like leaving your home village, only your village is a planet, and the neighbors might be plasma-based life forms. Still, the debate continues. Should we beam messages into space or stick to listening? Should any decision be made by scientists or by all of humanity? And how do you even organize a global vote without it descending into memes and arguments about biscuits? This leads us to consider one final, more human question. Regardless of whether aliens hear us or whether we hear them, perhaps the act of asking these questions tells us something useful about ourselves, about our hopes, our worries, and the kind of species we're trying to become. So let's imagine, just for a moment, that contact has been made. A signal arrives. It's verified, studied, rechecked by every observatory with a dish and a caffeine budget. It's real, not a pulsar, not a satellite, not someone microwaving soup in the observatory kitchen. Actual evidence of intelligent life. Now what? The first thing that happens is very little. International protocols suggest that the signal should be shared with the global scientific community before anyone makes announcements. So while the public waits for something official, hundreds of researchers are quietly panicking over whether they've accidentally discovered a message or just a very well-timed glitch. If it's confirmed as artificial, governments and agencies around the world are informed. In theory, this is when cool heads prevail. In practice, it's when diplomatic phone lines heat up, and every press office in existence starts drafting statements that say, "We're not saying aliens, but also maybe aliens." Eventually, the public is told. Not with flashing lights or someone shouting from a rooftop, but likely through a press release. Calm, cautious, slightly baffling. The message itself might be something abstract, a sequence of numbers, a repeating pattern, or a structured pulse that doesn't match any known natural source. It won't be, "Hello humans," in Morse code. More likely, 10-1-1-1-0-1-1-0-1-1-0, and a lot of debate about what it could mean. And then, things get a bit odd. The news spreads. The internet does what it always does: argues, jokes, panics slightly, and forms at least 3 conspiracy theories before lunch. Scientists, meanwhile, keep working. Is the signal a greeting, a map, an instruction manual, or just an alien equivalent of static? It might take years to decode, or we might never manage it at all. This isn't Hollywood. There won't be spaceships over London. No alien ambassadors shaking hands with world leaders. Just a signal from far away, and the knowledge that we're no longer alone, which frankly is enough. The psychological shift alone would be seismic. Every religion, every philosophy, every sci-fi writer with a "told you so" moment would have to take a breath. Some people might feel inspired, others unnerved. Some might not care much either way. After all, aliens don't exactly affect Monday's school run. But humanity, as a whole, would have to reframe its place in the universe. Not center stage. Not the only voice. Just part of a much wider conversation that's barely begun. This leads us to consider the final question. If the universe is talking to us, or waiting for us to talk back, what should we say? This leads us to one final, rather awkward question. If we did decide to send a message to aliens, what on earth would we say? It's not exactly the kind of thing you can scribble on a postcard. After all, we're representing an entire species. No pressure. The first hurdle is the language. Not English, not Mandarin, not even emoji. We'd need something aliens could plausibly understand. Numbers are usually the go-to. 1 follows 2, follows 3, unless you're doing your tax return. Mathematics seems universal, or at least less culturally confusing than trying to explain cricket. Messages like the Arecibo broadcast and the Voyager Golden Record tried this approach. Simple pictures, prime numbers, diagrams of DNA, and a polite hello in multiple languages. So far, no one's replied, which might mean no one received them. Or that aliens took one look and decided to pretend they weren't home. But if we could communicate, what would we actually want to say? Do we send a snapshot of Earth as it is, warts and all, or do we try to impress them with our greatest achievements? It's a bit like a dating profile, but for the galaxy. Do you show your Nobel Prizes, or leave out the bits about pollution, war, and reality TV? Some scientists suggest we should focus on shared knowledge, maths, physics, the structure of atoms. Others argue we should show our culture, music, art, philosophy. Perhaps they'd appreciate Bach, or perhaps they'd prefer silence. It's hard to say when you don't know if the recipient even has ears. There's also the question of tone. Friendly, curious, cautious? Should we sound eager, or play it cool? You don't want to come across too needy. Please talk to us, we're very lonely, probably isn't the vibe, but neither is, we've got nukes and we're not afraid to use them. Ultimately, any message says more about us than it does about them. Even if it's never received, it becomes a kind of self-portrait, a reflection of how we see ourselves, or how we'd like to be seen. Which might explain why these messages tend to be oddly optimistic. You don't tell the universe your worst bits, you tell it your hopes. And that's perhaps the quiet truth behind it all. Whether or not anyone's listening, sending a message into space is an act of belief. Belief that communication is possible, that curiosity is worth the risk, and that, even in a vast and silent universe, someone might care to answer. So far, we've explored distances, signals, silence, and speculation. But now we come to the quiet heart of it all. Why does any of this matter? If we're unlikely to meet aliens anytime soon, Why spend time thinking about them at all, especially when there's laundry to fold and an inbox full of unread emails? The truth is, this search isn't really about aliens. It's about us. About what it means to be intelligent, curious, and painfully self-aware creatures floating on a small rock. We scan the skies not because we expect quick answers, but because asking big questions is part of how we make sense of ourselves. Every time we consider other life forms, we hold up a mirror. We ask, what even counts as life? What do we mean by civilization? How would we explain ourselves to someone who's never seen a tree, or heard laughter, or eaten chips? Suddenly, our ordinary becomes worth examining. The search also gives us perspective. In a universe where stars are born and die in complete indifference, we're reminded that we're not the center of anything. And rather than that being depressing, it's oddly freeing. We're not under cosmic scrutiny. We're not expected to be perfect, we just are. And there's something deeply unifying in the idea that, to an alien observer, we are one species. They wouldn't care about our borders, our national anthems, or which side of the road we drive on. From their vantage point, we're all Earthlings, which is humbling and occasionally embarrassing. But perhaps, most importantly, the search keeps hope alive. Not the dramatic kind, but a steady scientific sort of hope. Hope that intelligence might not be rare, that curiosity exists elsewhere. That someone, somewhere, is also looking up and wondering if they're alone, whilst eating the alien version of toast. And even if we never find them, the act of looking changes us. It sharpens our questions. It reminds us how little we know. It keeps us grounded, even as we dream of other worlds. Because imagining the possibility of life beyond Earth forces us to look more closely at the life we already have here. This leads us, at last, to the edge of the great unknown. We've traveled across billions of years and trillions of stars, only to find that the next step, whatever it is, remains ours to choose. And that brings our journey to a gentle close. If you're still with us, you're welcome to drift off with another of our sleepy deep dives. Until then, rest well and good night.